Namaste students, welcome back to Rama Teaches You. Today we are going to do the second video on the E3 chapter of IB Physics. Okay, so the name of the chapter is what? What is the name of the chapter? Radioactive decay. Okay, so we are going to do the next video on this. So in the previous class, what did we do? We discussed about radioactivity, how polonium, uranium, thorium, and all of these are radioactive. We talked about the alpha decay. Okay, then we have this question here. Okay, let's start with the question. Radon 222 decays by alpha particle emission into polonium. Write down the nuclear equation for the decay. So, polonium is what? 218. It loses one alpha particle. Okay, one alpha particle means two protons and two neutrons. So, basically, radon 86 222 would result in the formation of polonium 222 minus 4 is 218, and 86 minus 2 is 84. So plus an alpha particle. Okay, this is how you can also write 2 and 4 here. So you will get a balanced equation. Okay, now calculate the ratio of kinetic energy of alpha particle upon the kinetic energy of polonium. Okay, assume that the radon nucleus is at rest immediately before the decay. Immediately. So we know that kinetic energy is given as what? Yeah, half mv squared, that is correct. But it can also be written as what? P squared upon 2m. Right? P is what? Momentum. P is equal to. So initially, the radon nucleus was at rest. So momentum initial is equal to 0. This will also be equal to momentum final. So P of alpha particle plus the momentum of polonium should be equal to 0. That is, P of alpha particle should be equal to minus P of polonium. Okay. Yeah. So basically, the ratio will become what? So P of alpha particle should be minus P of here. So the kinetic energy of alpha particle upon kinetic energy of polonium is equal to what? Hmm? P squared upon P squared of alpha upon 2 into mass of alpha upon P square of polonium upon 2 into mass of polonium. So if P of alpha is equal to minus P of polonium, if we square both sides, what do we get? P of alpha square is equal to P of polonium squared. So I can cut these two off. So E of alpha upon E of polonium is equal to 2 into mass of polonium upon 2 into mass of alpha. So this 2 and 2 can get cut off. So what will we be left with? Mass of polonium is how much? 218 upon mass of alpha is 4. So this can be 2 1s are 2, 2 zeros are 2, 9s are 18 upon 2. 109 upon 2. So the ratio will become what? 218 upon 4. So basically, they have asked about this ratio, right? Calculate the ratio. Ratio is this much only. 109 upon 2, or simply 109 is to 2. Okay? Okay. Or you can actually say 54.5 is to 1. Okay. Next. This means that the alpha particle accounts for about 98% of the kinetic energy of the decay produced. Okay? Now, let's move on. Practice question. Thorium 234 is a product of alpha decay. What? Is there anything that I missed? No, I had one question. They put here E. 6. Yeah. Yeah, E of alpha upon E of polonium, Akshay Pare, A upon B upon A upon D is what? D upon A. Clear? Okay. So that's what's happening here also. So you have the question number one. Thorium 234 is a product of alpha decay of an isotope of uranium. Write down the nuclear equation for this decay. So how will we write that down? So uranium, what is uranium? What is the 230, 230 uranium 235, uranium 238. Yeah. It's basically you can write it as uranium 238 and 92 will give us thorium 90 and 234 plus alpha 24. This will be the value after an alpha decay. Okay, calculate the number of neutrons in the parent nucleus of thorium. So, in the parent nucleus of thorium, how many neutrons are there? 234 minus 90. Okay, 144. Okay, next one. Americium 241 decays into an isotope of neptunium by an emission of an alpha particle. Okay, again, write down the nuclear equation. What do we get? Americium 95 241 will give us neptunium. 95 minus 2 is 93. 241 minus 4 is 237. Okay, neptunium plus alpha 24. This becomes the equation. Okay, then you have the kinetic energy of alpha particle is 5.5 mega electron volt. Estimate the kinetic energy of neptunium assuming that the americium is stationary when it decayed. So basically they're saying that the kinetic energy of alpha particle is 5.5 mega electron volts. Okay, we know that what kinetic energy in such a scenario when the decay happens, kinetic energy of alpha particle upon kinetic energy of um polonium, right? Sorry, neptunium should be equal to mass of neptunium upon mass of alpha. Okay, so basically mass of neptunium is how much? 237 upon mass of alpha is how much? 4. So basically 4 4 5 are 20, 4 9 are 36 point, 4 2s are 8, 5 59.25. Okay, so kinetic energy of alpha particle upon kinetic energy of neptunium is equal to 59.25. Therefore, they have given us the kinetic energy of alpha particle as 5.5 mega electron volts. Therefore, 5.5 into 10 to the power of 6 upon kinetic energy of neptunium is equal to 59.25. Therefore, kinetic energy of, do you have your calculator with you? Neptunium is equal to 5.5 into 10 to the power of 6 upon 59.25. What was the answer for this then, Akshay? 9.93 kilo electron volt. That is 9.3 into, sorry, 93 into 10 to the power 4 electron volt. Okay, that is the answer that we have. Okay, 9.3. Okay, next question. Next topic. The beta decay. How does the beta decay work? There are three variants of beta decay. They are as follows. First one, the emission of beta minus particles and electron. the emission of beta plus particles, a positron, or an electron capture. So let's see it one by one. What happens? A neutron in the nucleus is converted into a proton and an electron. The decay occurs in the nuclide with the ratio of neutron is to proton that is larger, and where therefore it is preferable to lose a neutron and gain a proton. Okay, so when the ratio of a neutron and a proton in an atom is very very large, what does that mean? It means that the atom has more number of neutrons as compared to that of protons, so it becomes more efficient for it to convert a neutron into a proton. So basically a neutron is a culmination of an electron and a proton. That is why a neutron has slightly more mass as compared to that of a proton. Okay, it is made up of an electron and a proton. So basically what happens is, when you have more number of neutrons compared to that of protons, a couple of neutrons actually get converted into protons and neutrons. Okay, the electron leaves the nucleus. The electron leaves the nucleus because confining the electron in a very small nuclear region would require enormous energy to be available in the nucleus. So electron cannot stay inside the nucleus with its proton. When a neutron breaks, it breaks into an electron and a proton, but the new electron cannot stay in the nucleus, so it comes out of the nucleus. This is not the case. This is not the case. So the electron leaves the daughter nucleus as a result of the interaction. A third particle is emitted as well. Unlike the alpha particles with two particles, this particle is known as an electron antineutrino, which has the symbol of VE dash. Okay, it's called an electron antineutrino. Okay, in terms of nuclear notation, the beta minus decay of thorium nucleus to protoactinium. Okay, protoactinium goes like this. So you will have what? You will have thorium gives you what? Protoactinium plus an electron, which is a beta minus, plus what? An electron anti-neutrino. Understood? An electron anti-neutrino. Now, basically, what is happening here? See, Akshay, look at this. Now, what is beta? Beta minus means what? An electron has gone out. Okay, so basically, what happens from 190, from the 90, you have gained an extra proton, thus becoming 91. So basically, thorium, you are becoming a new element altogether. Okay, yeah. Again, the equation balances because neutrinos are small particles with no effective mass or charge. Neutrinos are completely balanced in nature. Neutrinos do not require A or Z values, but if you include them, they must both be zero. Okay, what is important in writing its symbol to remember the bar over the Greek lower mu case? The significance that this electron antineutrino is an antiparticle. It's the opposite of a particle. It's like antimatter, Akshay. It's like antiparticles. Okay, so it results in the formation of an antineutrino. So a beta particle, a beta negative particle, and an antineutrino is sent out. Okay. Now, because there are three emitted particles in this equation, the daughter, the beta minus particle, and the antineutrino, there is no single solution to the momentum equation. The beta minus particles can have a range of energies unlike the alpha particles earlier. It was the observation of this beta energy spectrum that led to the discovery of the neutrino. This is discussed on page 638 HAL. Okay, that's not part of your syllabus. But for now, what is the thing that you need to take into consideration a lot? Okay, the thing that you need to take into consideration is that when you are splitting a particle into two, then it becomes easier for you to calculate what, when a huge chunk of matter is split into two, it is easy for us to calculate the momentum and the speed, the kinetic energy of the particles. because mass is being distributed. But in this case, that's not the only concern, right? The anti-neutrino does not have any mass. It is made up of pure energy. So you have to know with what energy level is this anti-neutrino coming out of the atom. Okay, with how much energy is this particle, this anti-neutrino, coming out of your parent atom? Okay, and after you calculate that, then and only then will you be able to calculate the rest. So it is quite a good this thing. Like it becomes a really good topic. One second. So this is the story of the beta minus particles. Okay. Now, what about the beta positive? Here, a proton is converted into a neutron and a positron. Okay, so basically, what is happening? A proton is getting converted into a neutron or a positron. As you might expect, it is observed in the nuclei that the proton rich, that are proton rich. The positron is the antiparticle of an electron with one positive electronic charge and an identical mass to that of an electron. Okay, so beta minus has the mass equivalent to that of an electron. The alpha has a mass which is equivalent to that of an electron, but the charge is opposite. So we call it a what? No, no. What is it? What do we call it? Positron. It's a positron. As you might expect, it is observed in nuclei that are proton rich. Where you have proton rich nuclei, you get to have a positron. The positron is the antiparticle of an electron with a positive charge and an identical mass to that of an electron. The third particle here is an electron neutrino. Okay, so you had an electron antineutrino here, and here you have an electron neutrino. This is the antiparticle to that of the electron antineutrino involved in the beta minus decay. The decay of magnesium 23 to sodium 23 is typical of this type of decay. The magnesium nucleide does not occur not naturally, but the daughter product is stable from form of sodium. So you had magnesium 23. What ended up happening? The magnesium lost one of the basically, how did it lose? So basically a proton is getting converted into a neutron. Okay, proton gets converted into a neutron. So the basically, when will this happen? In a nucleus where there are more number of protons. When there were more number of neutrons, you had a beta minus decay. When you have a nucleus with more number of protons, you have a beta plus decay. That is, you are trying to lose protons to become more stable because your nucleus is proton rich. But when you lose a proton, what happens? The atomic number decreases. So you get an element which is one step below, one step behind you. Okay, so huh? Hmm, that's a good question. One second. I think it gains an electron and then basically becomes a neutron, something like that. Wait, just help me. So, what happens, in my opinion, is that inside the nucleus, an, elect- an electron is created. Basically, what the Google says is that a quark burns itself. It flips. A quark. I don't know what a quark is. Okay, to be very honest. So I'll go deep into this. This is way ahead of 10th, 12th class Indian syllabus. Okay, so a down quark turns itself into an up quark. I think it creates an electron. So basically, nature does not allow you to create charge. Charge cannot be created, and isolated charge cannot be created. So basically, what I believe it does is it releases it makes an electron inside the nucleus, and to balance the law of conservation of charge, it creates a positron and it releases it outwards. Like for example, when a neutron was decaying, okay, if it had just created a proton, okay, if it had just created a proton, then the law of conservation of charge would have been violated, right? Yeah. So what it does it do? It releases a beta minus particle with a negative charge. So basically, even if you are creating a positive charge inside the nucleus, you are making sure that you are releasing outwards a negative charge to balance that extra positive charge that was created in the universe. Okay, so an extra positive charge was created in the in the universe. So to balance it out, you had to create an extra negative charge. I think that is the best thing that I can give you. Okay, explanation. I am in the process of learning quantum mechanics, but right now I am still learning structure of atoms Schrodinger's equation. Okay, I have downloaded a couple of books though. Okay, so if you ask me the same question in 6 months, I'll be able to answer you with more confidence. But for now, let's just leave the explanation till here. That is, universe created an extra electron. Okay, the universe created an extra electron so that a proton would basically get converted into a neutron. So to balance that, the universe also created a positron. Okay, and it released outside the nucleus. It created a positron or the beta plus decay, and when it was creating that, what does it do? It also creates a neutrino. Okay, it's a neutrino is created, and this neutrino does not have any mass or any charge. So it created a neutrino, and this is also known as what? What type of neutrino is it called? Electron neutrino. Okay, electron neutrino, and the previous one was called an electron anti-neutrino. Okay, anti-neutrino. Okay, and the third step is I think I did a good job explaining that. Okay, yeah. Am I right? Right? At least you know the basic. Okay, something happened because of which something happened. I'll go deeper into this and I'll explain to it much later. Okay, now electron capture, an alternative way in which a proton rich nucleus can increase the neutron proton ratio is to capture an electron. So, if you want to increase the neutron to proton ratio, what should you do? You should capture an extra electron. This electron and proton interacts to produce a neutron and the electron neutrino. Okay, so if you want to increase, right, if you want to increase the neutron to proton ratio, you will have to reduce the number of new protons. And how do you reduce the number of protons? By converting them into electrons, sorry, into neutrons. Okay, for any radioactive decay to take place, the difference in the energy between the parent and the daughter nucleus must be sufficiently large to permit the decay. Okay, in nuclides, the decay of electron by electron capture, the energy difference is small and the positron cannot be created. Instead, the nucleus captures one of the inner electrons from the atomic shell outside the nucleus. So it actually does not capture an electron from outside. But what does it do? It captures an electron from inside the atom itself. Subsequently, an outer shell electron replaces the captured electron. Okay, so an outer shell electron replaces the captured electron with the emission of a photon, a large energy usually in the x-rays. Okay, so what is happening here? To create this new neutron in the nucleus, one of the inner electrons in the atom had to go inside the nucleus. Okay,
Yeah.
so there was an empty space inside this nucleus. Now, we know that when an electron goes from a higher energy level to a lower energy level, it usually radiates energy, right? So, because there is an empty space in the inner shell of the atom, what happens is that an electron from the outer shell falls through the atom towards the inner shell, and during this process of falling down it is radiating energy. Okay, because to go from a higher energy level to a lower energy level, the electron has to release significant amount of energy. Now since it is going from the outermost shell to the innermost shell, the difference in energy levels is massive, and thus results in the formation of high energy x-rays. Okay, it releases in the formation of high energy x-rays. Now the equation for the electron capture process as argon 37 decays. Okay, argon 37 go undergoes what? It releases what, Akshay? So basically a neutron, a proton is getting converted into a neutron. Okay, so to convert a proton into a neutron, what do you have to do? You have to add an electron from the inside. Okay, so if you add an electron from the inside, what ends up happening? The atomic number decreases from 18, it goes to 17, and then you have 1737. And we know that the two atomic numbers of fluorine are 35 and 37, and 37 is pretty stable. Both of them are stable isotopes. So basically, argon should ideally have been argon 40, right? That is the stable atomic mass of argon, argon 40. But since argon 37 is an isotope of argon, it is pretty unstable. Now, it goes through this electron capture method. It releases, see, because it has used up an electron. What ended up happening? It used up an electron, an outer electron came inside, releasing what? It came inside and released some X-rays. Now, here we will understand more, where the outcome is a chlorine nucleus and the emitted electron neutrino. The emitted electron neutrino was emitted. Now, you might expect a positron capture process to occur. Although this would be symmetrical outcome equivalent to electron capture, it is not observed. It is not observed to occur naturally. So an electron capture method is visible, but a positron capture method is not visible. Okay. Now this was heavy. Okay. The electron capture, but did you understand the concept of electron capture though?
Yeah.
Okay.
So basically, difference between the one and the electron, like the electron one is beta minus one and is with the parent nucleus.
Yes.
With that, the positive, just negative. Next, just positive decays, like it will be added.
Beta positive decay. See it as positive beta decay or beta positive decay.
Beta. Yeah.
So beta positive decay would result in the formation of a neutron, and it is usually observed in atoms that have a large number of protons. So you get a beta positive decay. But did you understand what is being released? Beta negative is getting released. Why? Because you created a positive charge. Beta positive is getting released because you created a negative charge inside the nucleus. Okay, understood. So what is released when you have this beta negative decay? Negative beta decay releases what type of neutrino?
The
Electron anti-neutrino. That's the name, electron anti-neutrino. Now, when it is a positive beta decay, what is the neutrino that is released? Electron neutrino.
Yeah.
Electron neutrino. Okay, let's look at the question. Now, beta negative, write down the nuclear equation for negative beta decay of cadmium 113 into the isotope of indium. Okay, so beta negative decay results in the conversion of a neutron into a proton, right? it results in the conversion of a neutron into a proton. So basically, let's do this. You have cadmium 48 113 results in the formation of indium, and you have plus beta minus decay. This is what 1. Okay, beta minus decay, and then you have the anti-neutrino. And how, what is this? What is the symbol for anti-neutrino? VE dash. VE dash. Okay, so an anti-neutrino is released. Now, what happened here, Akshay? You had 9 in beta negative decay. What happened? The atomic mass was the same, but the number of protons increased by 1. In beta positive decay, what happens? The atomic mass remains the same, but the atomic number decreases by 1. Okay? Okay, so here indium is going to have what is the this thing going to be? 113, and instead of 48 you will have 49. Very good. Okay, minus 1. Okay, minus 1 beta minus. Okay, I don't have to write a minus here though. Okay, now next, the positive beta decay of oxygen 15 into the isotope of nitrogen. Okay, so you have oxygen 8 15. Okay, beta positive decay, the number of protons is going to decrease. The atomic mass is going to remain the same. So we'll have nitrogen 7 15 plus beta positive plus neutrino, electron neutrino. Is this the same? Exactly the same. Okay, beta 1 positive. Okay, next. The final one is the electron capture by iron transmuting into an isotope of manganese. Okay, how does this happen? The atomic mass again remains the same, but in an electron capture, the number of protons decreases. Okay, the number of protons decreases. Okay, so you will have what? Iron 2655 gives you what? Sorry,
No, you are eight.
plus beta minus 0 would result in manganese 26 becomes 25 55 plus a electron neutrino. Okay, next, thorium 23490 decays into protoactinium 23491. State 2 remaining decay products of thorium 234. So basically the atomic number increased, so it will be a beta minus 1 0 decay, right? Because a neutron got converted into a proton, so the rest of the two will be what? It will be a beta minus 1 and an anti-neutrino. Okay, anti-electron neutrino. Understood?
Yeah.
Okay, next. Oxygen 18, 8 to 18 is formed when an isotope of fluorine F minus decays with an emission of a positron. Okay, so beta positive is a positron. Write down the nuclear equation for the decay. Okay. Fluorine
And 18 is
9 18 beta positive I have to plus beta.
No, it's not this. It's for the electron.
Yeah, I got it. Gives you what? Oxygen 8 18 plus a beta positive 0 plus a electron neutrino. Here, is it correct?
Yeah.
Okay, let's move on. The gamma photon emission. So we have already discussed about the alpha decay, the beta decay, In the beta decay, you have three different types. That is the beta negative decay, the positive beta decay, and the electron capture method. Right? These are the three ways that you have possible. Now, when you have the gamma photon emission, now what happens in the gamma photon emission? A daughter nucleus is often left in an excited state after alpha or beta decay. Okay, let's see. A daughter nucleus is often left in an excited state after the alpha and beta decay. An excited state is one in which the nucleus has a surplus amount of energy relative to the state of lowest energy. The following decay schemes in part is part of the path that begins with the neutron bombardment of naturally occurring cobalt 59. Okay, now what happens here? Finally, see, basically you have cobalt 2759. You are releasing, you are adding a neutron. Basically, neutrons are being bombarded onto this. So what happens? Okay, so you'll be left with 2716. So basically, you had one neutron added to your cobalt 59 atom. Okay, so it became cobalt 60, but this is what does this M indicate? Hmm. So students, let's do one thing. Let's continue this in the next video. Okay. So please subscribe to my channel to watch the next video. And if you like this video, please do like, share, and subscribe. I will explain this to you much in more detail in the next video. Thank you and have a nice day.